Good day, ladies and gentlemen. This is MTS 102 class, Introductory Mathematics 2. Today we are moving to another section, which is a techniques of differentiation. Techniques of differentiation. Here is the objective of the techniques of differentiation. That is, on completing this section, you should be able to work on differentiation of sum, difference, product and quotient, differentiate parametric functions, and also differentiate implicit functions. Here are the contents of the topic. That is, we have a differentiation of a constant, differentiation of sum, difference, product and quotient, differentiation of parametric functions, and differentiation of implicit functions. The introduction. In mathematical analysis, techniques of differentiation explores various rules, including the product, quotient, chain, exponential, and logarithm rules. That is, under this we have a product rules, we have quotient rules, we have chain rules, we have exponential rules, and also a logarithm rules. So here is the learning outcomes. Now, differentiation of a constant. Differentiation of a constant. In this theorem, we're going to see how we can differentiate a constant. How we can differentiate a constant. Let's look at this theorem. The derivative of a constant is 0. I believe you all know that the derivative of a constant is 0. Let us prove it. Let y equal to f of s equal to c, where c is a constant. Then y plus change in y equal to c. Y plus change in y equal to c, that is the small increment in that y, is what you are having as change in y there, which is equal to the constant c. Therefore, making the change in y the substitute formula, we have this as c equal to c minus c. That is, we have the function given as c. The function f of s is equal to c. So you replace it here where you have y. That is why we are having it as change in y equal to c minus c. And c minus c is 0, is equal to 0. So that is the proof here. You can see that the derivative of a constant is 0. So now see that change in 1 over change in s is equal to 0. That is the proof. We have been able to prove that. Let's go on. Now we move to the differentiation of sum, difference, product, and quotient. Differentiation of sum, difference, product, and quotient. All these we are going to be looking at it one after the other. New functions may be constructed from any two given functions f and g by forming their, that is, Roman figure 1, form their sum, that is, sum of f plus g. That's the sum f plus g. Then look at the difference here, which is in Roman figure 2. Difference f minus g. I believe we all know what difference means. That is, you subtract G minus F, F minus G. Also, number figure 3 is the product, which is the product rule. FG, this product means multiplication. Product FG. And also number figure 4, we have quotient. We have quotient, that is F over G. So quotient in fraction, F over G. So at this point, we want to give some set of rules which enable us to find the derivatives for sums, differences, products, and quotient of functions. So we now taking it one after the other. That is to find the derivative for sums, differences, products, and quotient of functions. Let f and g be two functions. Taking f and g as two functions now, then f plus g prime of s, f of g prime of s, that is, we want to differentiate this now. This is sum of f plus g. Let's differentiate it. We have it as the f ds plus the g ds. That is the sum rule. That is the rule that guides that. The sum rule. So let's go on. Number 2, we have that of difference. F minus g prime of x, f minus g prime of s. The difference rule now, we have the f ds minus the g ds. The f ds minus the g ds. That is the difference rule. Then number 3, we have the product rule, fg prime of s, fg prime of s, and this is how it is formed. We have it as f of s the g ds plus g of s the f ds. That is product rule. Then number 4, we have f over g prime of s, f over g prime of s. That is the quotient rule. And look at it how it is being formed. G of s the f ds minus f of s the g ds all over g square of s. That is the quotient rule. Is the quotient rule. So in some textbooks, you can see it as if you are representing your f as u and you are representing your g as v, then some textbook will give you as v du ds minus u dv ds all over v square. So but for here, we are representing it as f over g prime of s, and our own outcome here is g of s the f ds minus f of s the g ds all over g square of s. That is the quotient rule. Now let's move to the example. We are starting from the sum now. Starting from sum, where we have find the y dx if y equal to 7s raised to the power 3 plus 3s squared minus 5s plus 4. So let's now differentiate this. We have the y, the s is equal to d the s of, the y we are given is, the value of y we are given is 7s raised to the power 3 plus 3s raised to the power 2 minus 5s plus 4. So if we are differentiating it, then we declare it as this. The y ds equal to d ds into 7s raised to the power 3 plus 3s squared minus 5s plus 4. That is our y. This is the, we now separate it. We can separate it as this, where we have d ds of 7s raised to the power 3 plus d ds of 3s raised to the power 2 minus DDS of 5s plus DDS of 4. So you are differentiating it separately here. And looking at it, if you differentiate that of 7s raised to power 3, so we have it as you multiply the power by what you are having as constant there, the constant of x. So it gives us what? 7 multiplied by 3 s raised to power 2, because that power of s, which is 3, will be minus 1, 3 minus 1, and we are left with 2. So that's why we are having it as 7 into 3s raised to power 2. Then the next one is ds of 3s squared. Let's differentiate that. 3s squared. If we are differentiating 3s squared, it gives us what? You multiply the power by the constant here, which is 3. Then we now have it as 2 multiplied by 3 s raised to power 2 minus 1. So the answer will be 3 times 2s, that is, we have it as 6x there. Then also we have DDS of 5s, DDS of 5s. Let's differentiate 5s there. We have it as 5s, that is raised to power 1 minus 1, 1 minus 1. And s raised to power 0 is 1. Whatever variables that are raised to power 0 is always 1. So here we have 5s raised to power 1 minus 1, which is 5s raised to power 0, and it becomes that s raised to power 0 is 1. So we have it as 5 into 1 there. And we want to differentiate DDS of 4 here. Differentiate that constant 4. You know, we've been told that differentiation of a constant is always what? 0. So if I differentiating this constant, which is 4, it will give us 0. That's why we're having it as differentiation of 7s raised to power 3 is 21s squared, and that of 3s squared will give us 6s, and that of 5s will give us 5, which is 21s squared plus 6s minus 5. So that is the answer to that. We've gotten the answer as 21s squared plus 6s minus 5. Now the next one, we have this question: differentiate y equal to sine s plus cos s with respect to x. Y equal to sine s plus cos s with respect to x. Let us look at the solution. The dy dx, you know it is with respect to x. Now have it as dy over the x of what? Sine s plus the s of cos s. You know the question given is differentiate y equal to sine s plus cos s, and we want to differentiate it with respect to s. Now let's pick it one by one. We now have it as dds of sine s plus dds of cos s. So if we differentiate sine s, it gives us what? Cos s. And if we differentiate cos s, it gives us what? Minus sine s. So the answer here is now cos s minus sine s. That's the answer to that. Then we move to another example where we have it in number 3 here. Differentiate y equal to 3s plus 1 in brackets and also 5s plus 3. If you can see this, we are moving to product now. The product, you know, the one we have been solving is sum. It is the addition, the sum. That is the sum rules there. Then here we want to practicalize the one we're having as a product rule here now. Look at it, we have a differentiate y equal to 3x plus 1 into 5x plus 3. So here we want to represent the first bracket, the one in the first bracket as u and the other one as v. Where we have 3x plus 1, we represent that one as u, and where we have 5x plus 3, we represent it as v. So that's why we have it as let u be equal to 3x plus 1 and v equal to 5x plus 3. Then the y dx will now be equal to u dv ds plus v du ds. So that is the product rules we are employing here. The y ds is equal to u dv ds plus v du ds. Now, if we first of all differentiate u here. That we differentiate it as du ds. We also differentiate v as the v ds. So that's why we're having the u ds is equal to 3. If we differentiate 3x plus 1, we're going to have 3. That is where we have the u ds is equal to 3. And we want to differentiate the v ds, where our v is equal to 5x plus 3. So let's differentiate it. The v ds is equal to 5. Is equal to 5. You know that 3 is a constant, it becomes 0, and that the one 3x plus 1, the one there is a constant, is also 7. So we only differentiate that of 3x and 5x. So the answer for the u ds is equal to 3, and the answer for the v ds is equal to 5. Now we want to make use of that formula now. Where you see u, you represent the value of u there. Where you see the v ds, you substitute the value. And also where you see v, you write the value of v, and where you see the u ds, you put the value of the u ds. That is what we did here. So the y ds is now equal to 3x plus 1 5 into 5 plus 5x plus 3 into 3. Then we now evaluate. We evaluate, then we have our answer as 30x plus 14. If you use 5 to open this bracket and you use 3 to open the other bracket, then we are going to have 30x plus 14. That is the answer. That is the answer. Then also under this product rule again, we have differentiate y equal to cos x sin s. We differentiate y equal to cos x sin s. So if you can look at this question very well, you see it is a product of two functions there, where we have cos s and sin s. So let us look at the solution. We now represent cos s as u, and we represent sin s as v. So let u be equal to cos s and v equal to sin s. Then the u ds will give us what? If we are differentiating cos s, we're going to get minus sin s. And if we are differentiating sin s, we're going to get cos s. That's why we're having the u ds is equal to minus sin s, and the v ds is equal to cos s. Therefore, the y ds will now give us, we are applying the formula here now. You know, we have the formula as u dv ds plus v du ds. So we now substitute back to that formula. Then we have it as u, which is cos s, into the VDS. We know the VDS is cos s, so we now have it as cos s into cos s plus, then also v, the u, the s, and we have it as sin s into minus sin s. So you open the bracket, you have cos square s minus sin square s, and cos square s minus sin square s is equal to cos 2s. It is equal to cos 2s. That's the answer to that. Then we move now to another example under the quotient rule. So you can see that this one now, this example is in fraction. It is in fraction. You know, we have done that when you are talking about quotient. Then you are going to have that question in fraction. So we have it here. Find the y, the s if y equal to s squared plus 1 all over s squared minus 1. So what do? We represent the numerator as u and we represent the denominator as v. So look at the solution. Let u be equal to s squared plus 1 and v equal to s squared minus 1. Then the u, the s is equal to 2s. We differentiate the u, the s, that is the numerator, where we have s squared plus 1. Let's differentiate it. Is the u, the s is equal to 2s. Is equal to 2s. And also the denominator, where we have where we represent it as s squared minus we represent that one as v, which is s squared minus 1. So we now want to differentiate it. It is the v, the s, which is equal to 2s. The v, the s is equal to 2s. So we now go back and substitute back to the formula. I believe you know the formula for quotient. You know the formula for quotient rule. The formula for quotient rule is v, the u, the v, the s. We have v, the u, the s minus u, the v, the s all over v squared. All over v squared. Since you know that we're representing this as u and v, so we now have the formula as v, the u, the s minus u, the v, the s all over v squared. So we just substitute back to that formula. Where we have u, we substitute it. Where we have u, we substitute the value. Where we have the v, the s, we substitute. Where we have the u, the s, we substitute. Then also where we have v squared, we substitute the values. So that is what we are having here as the y, the s is equal to s squared minus s into 2s minus s squared plus 1 in bracket into 2s all over which is v squared, that is s squared minus 1 all squared. So if we expand and work it out, then the answer we are going to get is minus 4s all over s squared minus 1 minus 4s all over s squared minus 1. So that is that. We're now moving to differentiation of parametric function. Differentiation of parametric function. I believe you have heard about parametric function before. You have heard about parametric function. A parametric function is a type of function where the output variables are defined in terms of a parameter. So let me repeat myself. You can, when you get to this point, you can put it down. A parametric function is a type of function where the output variables are defined in terms of a parameter, and the parameter is often represented as t. So if you look at what we are having here, if y equal to y of t and s equal to s of t, define y as a function of s. We can write t equal to t of s. We can write t equal to t of s. You know, from that definition, you can see that we often represent it as t. So we can have it as t equal to t of s, so that the y dt is equal to the y dt dot dt the s. That is the y dt multiplied by dt the s. is equal to, we can also have it as dy dt divided by ds dt. So any time we are given any question on this parametric function, so this is how we are going to go about it. So let's move on. We now have this example under this parametric function. So if y equal to t squared plus t and x equal to t raised to power 3 plus 2 raised to power 2, find dy dx in terms of t. Find dy dx in terms of t. We are given function of y there, and we are given functions of x there. So now we are now going to find the y dx in terms of t. Let's start. Look at the solution. Now the y dt, you know, we are given y as equal to t squared plus t. So let's differentiate that with respect to t now. Let's differentiate this y, which is equal to t squared plus t, with respect to t. Now the y dt will be equal to 2t plus 1. If we differentiate t squared, it's going to give us 2t. If we differentiate t, it's going to give us 1. Because t raised to power 1 minus 1 is t raised to power 0, and t raised to power 0 is 1. So that is the derivative there, which is 2t plus 1. And we want to differentiate x now with respect to t, and the x given is equal to t raised to power 3 plus t raised to power 2. So now let us differentiate it with respect to t. We now have it as the x dt is equal to, differentiate t raised to power 3, it will give us 3t raised to power 3 minus 1, and we are having it as 3t squared. That is, if we differentiate t raised to power 3, it is going to be, you use that power to multiply that variable there. We have it as 3t raised to power 3 minus 1, and it is going to give us 3t squared. And we want to differentiate t squared now. We are going to have a 2t raised to power 2 minus 1, and it's going to give us 2t. You know, 2 minus 1 will be 1. So it is going to be 2t, that is raised to power 1. So it's only that we're not writing the power there. So it is 2t. So we have gotten the y dt now and the x dt. So going back to that formula where we have the y dx. So the y dx is equal to the y dt divided by the x dt. So since you have gotten the y dt and you have gotten the x dt, so just place the value there and divide, and we have 2t plus 1 all over 3t squared plus 2t. And what comes to the denominator is t. That's why we're having t outside there. And the answer is 2t plus 1 all over t into 3t plus 2. So that is the answer to that. We have gotten that solution under the parametric function, differentiation of a parametric function. So let's now check this example again, where we have if y equal to 2 sin theta and also x equal to 3 cos theta, find the y dx. Find the y dx in terms of theta. And you should all know that y is given here in terms of theta, x also is given in terms of theta. So we now want to find the y dx in terms of theta. So just the way we approach the first example there, so we are going to get it just the same way. Now the y d theta now You know, the other one is given in terms of t, and this one is given in terms of theta. So we are going to differentiate with respect to theta. So we now have it as the y theta is equal to 2 cos theta, because 2 sin theta, if we differentiate it, it's going to give us 2 cos theta. And the s d theta, where we have s is equal to 3 cos theta, we are differentiating it now. We have it as the s d theta is equal to minus 3 sin theta, is equal to minus 3 sin theta. If we differentiate 3 cos theta, it will give us a minus 3 sin theta. Since we have gotten that now, we just need to substitute to the value where we have the y, the s equal to the y d theta divided by the s d theta. Substitute the value, then you divide. We have the answer is minus 2 over 3 cos theta. You know, cos theta over sin theta will always give us what? Cot theta. Go and check the trigonometry identity there, then you will see what I'm talking about. So 2 cos theta over minus 3 sin theta is equal to minus 2 over 3 cos theta. So let's go on. We now move to differentiation of implicit function. Differentiation of implicit function. By the way of an example, let y be divided by implicitly. Let y be divided implicitly by x squared plus y squared equal to 1. So we are going to use this now to explain what we mean by differentiation of implicit function. Now, x squared plus y squared equal to 1. Differentiating each term with respect to s. Differentiating each term with respect to s, we obtain this. So now we have it as the s, the ds of y squared plus ds of s squared is equal to ds of 1. That is, pick s squared, we differentiate it. Pick y squared, we differentiate it. And also the constant 1, we differentiate it. But this time around, with respect to x, with respect to s. That's why we are looking at it here as ds of y squared plus ds of s squared plus ds is equal to ds of 1. Now, if this one implies ds of y squared, you know, this function, the function y squared here, we are differentiating it with respect to s. So we now have it as ds of y squared. If you differentiate x squared with respect to x, we are going to have it as 2s. We differentiate that, which is equal to 0, and differentiation of constant will give us 0. Now, notice that y squared is a function of y. Y squared is a function of y, which itself a function of s. It is also a function of s. So therefore, we are going to differentiate that y squared, having it as 2y dy ds. Since y is a function of s, so we are differentiating it as 2y dy ds plus, you know, we have gotten the differentiation of s squared as 2s, which is equal to 0. So this one now implies that we are going to make the y ds now the subject of the formula. We're going to make the y ds the subject of formula. We now have it as the y ds is equal to, then we have it as 2s minus 2s divided by 2y. If we divide it, we are going to get minus s all over y, minus s all over y, because 2 will have cancelled out. So we are left with minus s all over y. That is implicit differentiation of implicit function. That is differentiation of implicit function. In general, to differentiate a y function with respect to s, we differentiate it with respect to y, and then append the y ds, just like what we just the example we just concluded. So you know, by the time you differentiate that y, then you append the y ds. So for example here, for example, let's say look at this example where we have to differentiate yn. When we have to differentiate yn, you know, we have it as dds of y raised to power n, dds of y raised to power n. If we differentiate yn here, we are going to get it as ny, that is the power there, which is n. We multiply it by the variable, which is the function of y there. We now have it as ny raised to power n minus 1, then you append the y ds. You append the y ds. So I believe you have now understood what is called the differentiation of implicit function. That is how we go about implicit function. Anytime you are given question like that and you are asked to differentiate in that form, so that is how you are going to go about it. So with this now, we have come to the end of today's class, and I believe we have been able to walk through the differentiation of implicit function, that of where we have the product rule, sum rules, difference rules, so, and also quotient. We have done that. Go through it again, check it, and you will see that everything is well explanatory. Thank you for listening, and we'll see you again. Bye for now.